All right. We're going to talk about domain or range specifically and an area function. Okay. So Paul's a farmer and he has 24 meters of fencing to enclose a garden he has. Okay. But this garden is going to kind of back onto the wall of his barn. Okay. So we'll use red to represent the wall of the barn. Okay. And this fencing is essentially just going to be three-sided. We're going to use the wall of the barn to help us out here. That way we don't have to use all of the fencing, have a much smaller area. We want to try to maximize this as much as we can. Okay. Now, because it's 24 meters of fencing, the fencing is considered the perimeter of the garden, right? And we know the perimeter of the garden, so we'll call it P. The perimeter is a function of the width, okay? And actually so is our area here. What we'll say here is a perimeter, so P at X is equal to, and we know P at X is actually equal to 24 meters, but we don't know what's going to represent what. Because it's a rectangle, we know that these two sides are going to have to be the same. So what we'll do is we'll call them X, okay? We'll call both of those X. Now this length here, we kind of have to figure out what can we do with this length, okay? We know that if we were to represent this as perimeter, we'll call this L. Perimeter would equal 2x plus L. And we know the perimeter itself is 24 meters, so 24 is equal to 2x plus L. Okay? But the problem is we want everything to be a function of x. We want it to be in function notation. We want our only variable to be the x variable. And right now we have an L involved. So what I'm going to do is I'm going to set this equal to L, this equation. And I'm going to replace L with an equation that only has the variable x in it. Now this isn't something we need to know how to do. I'm just kind of walking you through the process of how they built this. Okay? So in other words, I'm going to isolate for L. And if I do that, I get 24 minus 2x equals L. Okay? So what that's saying is I no longer have to put L here. What I can put is 24 minus 2x. That represents this side of the fence. Okay? That concept, if you don't understand it, that's okay because it's not imperative for what we need to know right now. But I just want to show you how they got where they did in this little example. Okay? So we have all this information. Let's redraw this little fence we have. Okay? So our fence, because it was limited, because our perimeter was limited, we only had 24 meters of fence. This side is going to be x, so this side is going to be x, and this side is going to be 24. Subtract 2x, right? 24 meters, subtract the two widths, and that's how much length we have on this side here. That kind of makes sense in terms of what we have. So what we're going to do is we're going to make an area function. We want to figure out what the area of this could be. And the reason this is x is because I can make these widths any numbers I want. I can say it's 1, or it's 2, or it's 3. I have many options. It could be 2.5, anything in between, right? So if I were to find the area of everything in here, okay, the area function would say that the area with the variable x, so this is our function notation, is equal to, well, area is the width times the length, right? So that's x multiplied by 24 minus 2x, okay? And what we can do here is, do you remember distributive property?
Yeah.
So use our distributive property to come up with our function. And our function, and I'm going to put this value in front, it's going to be negative 2x squared plus 24x. Does that make sense? So this is like the standard form of that function. We have it here, okay? Now, what we kind of need to do is we need to put some parameters on this fencing. We need to figure out what the minimum side width and the maximum side width can be, because we only have so much fencing, okay? And what I mean by that is, can I decide that this side is going to be negative 1 meter? Is that possible?
No.
No, that doesn't make sense. In fact, can I say it's going to be 0 meters?
No.
No, I don't have a fence then. So that's the idea. We know we're going to have a perimeter of 0. Or sorry, not a perimeter, but a parameter of 0. 0 is going to be one of our negative, or sorry, our low point. And can I say that this side is going to be 24?
Yeah.
Yeah? If I made that 24, would I have any room for this fencing over here?
No.
Everything would be used up. So 24 is way too high of a number, especially since I have to duplicate that on the other side. I need 24 and 24. Already I need 48 meters of fencing, and I only have 24. So we know 48 is a number that's way too high. So we want to figure out what an option is, okay? So in other words, because this is a quadratic, we know it has some relationship like this, okay? It does, and actually because it's a negative quadratic, do you know which way it faces?
Upward.
Yeah, so it does this type of motion, okay? So we're actually opening downward in this case, okay? Our lowest point is going to be 0. We know 0 is one of them, and we got to figure out what our highest point can be. In other words, the x-intercepts. And those are where our area, this is our x-axis is our area, whose area will be 0. Okay, sorry, this is our area. And this is our width, our x, on the x-axis. Okay? So, if we were to kind of factor, we'd actually go back here. This is like a factored form. Okay? So we need to find where area is 0. So we set area equal to 0 is equal to x times 24 minus 2x. Okay? Well, we know that when we're multiplying to create an x, one of these two must be x. So we split the equation. Okay? We know that x must be equal to 0 and 24 minus 2x must be equal to 0. These are going to be our two x-intercepts. And we already know one of the x-intercepts is when x is 0. That makes sense, right? The other one, we solve for x here. So I bring 24 over. I get negative 2x equals negative 24. Okay. And I divide by negative 2. X is equal to 12. So our other parameter, our x-intercept, is at 12. And this one, so 12 and 0 and 0 and 0. These are our x-intercepts of our parabola. So in other words, our parameters for this fence, okay, well, we know that x can be every number in between these two values. So we say x is the element of all real numbers. That's what this stands for, every number in between. Okay, but x has to be greater than, what's our lowest point? 0. Can it be equal to 0?
Yeah. No.
Not in this case it can't, right? Because if it is, then I don't have a side of a fencing. And it has to be less than what value?
12.
Can it be equal to 12?
No.
No, because if both of these side lengths are 12, that's 24 right there. I have nothing left for the length, right? So those are the parameters to this part of the fence. So my domain here is XER, such that x is greater than 0 but less than 12. Okay. What about our range? Okay. Technically, the range could be anything we want, right? We could have an area. Can I have an area that's below 0?
No.
No. So we already know we have a parameter with the range also. The range, we'll put that in blue, we'll say. We know y can be an element of all real numbers because it's a continuous function. But same idea, our y has to be greater than 0. And it also has to be less than a number. What number does it need to be less than? What's this point?
24.
Oh, is it 24? I actually don't know what it is off the top of my head.
No.
Yeah, it's going to be an area of the function.
Oh, okay.
So this is the max area, right? We don't know what it is off the top of our head here. We know that with these two x-intercepts, so let's use axis of symmetry to solve it, okay? What would be right in between 0 and 12?
6.
6, right? So we know our axis of symmetry is at 6, okay? And then if we plug 6 into this equation here, okay, or into this equation here, this is the standard, this is the factored, it doesn't matter what you do. I'll just bring up a calculator really quickly. Okay, let's do it into the factored form here. This says 24 minus 2 times 6. What's 2 times 6?
Negative 2 times 6? Or?
Yeah, negative 2 times 6.
Negative 12.
Yeah, okay, you know what? I can do this all by pencil. So this becomes 6 times, negative 2 times 6 is negative 12, so that's 24 minus 12, right? 24 minus 12 is 12 times 6. And what is 12 times 6 in this case? Ends up being 72. So what it's saying is our max area, so the max area would be 72 if we made the widths both 6 meters, okay? So if both of these are 6 meters, that'll make this 12 in length, and our area is 72, and that's where we max out. On the way up to that, all of our areas are less, and after that, all of our areas are less. Okay, so that gives us a parameter. We know y has to be greater than 0, and it must be less than
6.
Actually, because it's the y value, we're looking at this number here.
So 72.
Yeah. Now, in this case, can it be equal to 72?
Yeah.
It can be. It definitely can be equal to 72. But we can't have an area of 0. So this is the only case where we use that equal to sign. Okay? And all the other ones, it had to be greater than and less than with no equal to. This one is greater than and then less than and equal to the number 72. Does that make sense for the domain and range of those two functions? All that other work is, we'll get into more of it later. It's more of a recap of the grade 10 stuff, and I know it was a bit confusing, but really we're just focused on what were plausible areas of this fence. That was what was most important. And we discovered that the widths of the fence can only be between 0 and 12, and the areas could only be between 0 and 72. Make sense?
Yeah.
Okay, good.